Hello, everyone. Welcome to this week's binary episode of the Day Zero podcast. I'm Spectre, with me is Z. In today's episode, we have a bunch of Windows bugs and a Weston Embedded mem corruption. Before that, though, I'll let Z cover the spot the Vuln that was up for this week and last week.
Yeah, and this spot the Vuln was one that we used quite a while back. I didn't go and dig up exactly how far back it was, but it actually came from a 0-day initiative post where they were talking about an incorrect balance check or balance calculation within the eBPF verifier code on like Linux 4.9 something. I'm not sure what the minor version there was. Uh but so the spot the vuln code, technically it is a binary issue. Uh but it has, or at least to spot this bug, it's very much just look at what logically this should be doing when it's trying to calculate these min values and max values. So the LSH code is all correct, and I'm just going to walk through it here very quickly. We've got the case BPF LSH, and as it's going through, it has kind of its edge case, and then when it's trying to calculate what is the minimum possible result of doing the BPF, and I guess I should explain, this is part of the eBPF verifier code, so it's basically walking through whatever BPF program you give it, and trying to make sure that, and I think it's during a separate pass that it's going to look and make sure like there's no loops in the code, so you can't like deny service through one of these programs, and also that like there are no memory potential like memory corruption issues going on within it also. So that's what this code is doing, or part of, where it's just tracking the minimum and maximum values to make sure nothing ends up going out of range. So what we've got here is it's calculating the minimum value. It's doing a shift, and this is the left shift. So when you have a left shift, and that is a bitwise operation, the minimum value is going to be like you take the minimum source value or like original value and you shift it by the minimum number of bits to the left that it has within its ranges. Which you'll see here, it's saying min value left shifted by min value, so that makes sense. And to get the maximum value with a left shift, you're going to take the highest starting value and shift it to the left by the maximum number of bits. So again, that makes sense. Now, whoever wrote the RSH code, it looks like they likely just copied and pasted a lot of this code over and just pasted it right in, because you have kind of that same structure, same format. And what they do is kind of the same here, where they take for the minimum value, again, they're taking the min value and this time right shifting it by the min value. And for calculating the max value, they're again right shifting it by the max value, which is just mirroring what the left shift did, except for a right shift when you're shifting all the bits to the right. That doesn't work. What you'd actually want to do is for the maximum value, you'd want to take the maximum starting value, but because the right shift makes the value smaller, like dividing by 2 for every shift, you would want to shift it by the minimum number of bits. So you would actually want that to be the minimum value there, not the maximum value. So they're basically doing their balance checking incorrectly there. And also for the min value, you would want to shift it by the maximum number of things to get it as small as possible. So basically these max and min values end up being incorrect, which can then allow for eBPF code that actually does do things that would lead to a memory corruption, allows them to pass through. So it's bypassing the check, but the main thing to look at in terms of spotting this is just logically is what it's doing, is what it's trying to do correct. In this case, it is not getting the right minimum or maximum value, and it has kind of that logical aspect rather than being a purely memory corruption issue. In context, this results in memory corruption, but just at the code level, you would just be thinking like, does this make sense at all for it to shift it in these ways to calculate what it thinks is a min or max value?
The memory corruption isn't immediate,
Yeah,
so it's a little bit hidden, so to speak.
yeah, it would happen much, much later, because it would happen when the actual program ran versus just getting through the verifier.
Yeah. And speaking of overflowing memory corruption, we have our first topic from Talos, which is an off by one out of bounds write issue. in Weston Embedded UC HTTP, and I'll let Z get into this one.
Yeah, and this one is relatively straightforward and has kind of a code pattern that you see a lot. As the title indicates, this is parsing the host header. You've got the potential corruption, and that just comes down. It's got this HTTP rec header parse value get function. Nice long name. Going there that tracks the or ends up getting kind of the length of what it would be. That gets written into the length. It goes and formally writes out using either the length that it got from there or just the configuration for whatever the name of the host name, the maximum length should be, gets whichever one is smaller from that, as what the actual length is going to be before it does the proper copy. So that way it's just not copying too much data. Or that way it's not copying too much data into the actual connection object, pcon object. And then the last step of this is that it goes and just adds in a null-byte to that length value. So the problem here is that the where it's copying all the data into that host pointer, that is allocated to be host name len max bytes long, which makes sense. And that's kind of, in theory, what they're checking against is they do the check, they do the def min, so they're getting that right. The problem is when you go in and do this access on host pointer, that's accessing it at length. So that is potentially, if you give it a long host name, that is potentially accessing it at host name len max, which is going to be one larger than the actual largest index you could use. So this ends up being 1 byte out of bounds because it should be either length -1 or doing the -1 somewhere else. But because it starts, the first index is 0, going up to that and not actually having the index of that value, they're just writing their null byte 1 byte out of bounds, which is a relatively common just off by 1 error to make. It's one of the more common ways you'll only see that issue come up is in just making the mistake of thinking the amount of bytes you allocate is also the last index you can use. And sometimes it doesn't really do much or doesn't have much impact because the actual allocation ends up being a little larger anyhow, so nobody ever really notices it. But in this case, that 1 byte out of bounds within their kind of memory pool, so they're using their UC lib memory system here that has kind of its own allocator, and that allocator happens to store metadata inline, similar to like ptmalloc or something. And importantly, what it'll store in the very first bytes of a free block is the pointer to the next free pointer. So you get very much like if you're familiar with the ptmalloc or glibc allocator attacks, like a House of Spirits style attack, so you can get out of this. You're able to, so I guess it is only writing the single null byte, so you're able to basically overwrite whatever that pointer was and just write the least significant bits to 0. So that gives you that partial overwrite into 0, which is likely going to be within the same memory range that everything else is, because you're only overwriting or kind of rounding off those couple bytes, so it's likely that you'll be able to gain or coerce control of just that rounded, or the aligned, I guess I should say aligned actually, that aligned size. So that block should be within attacker control, should be something they can get control of. So then when it goes to dereference what that free pointer is, that is going to be dereferencing an attacker controlled location, puts that, or not puts that into the list, but basically treats that as the next block to give out. And so you get an allocation, add in attacker controlled location, anywhere you want, give you more or less arbitrary read write from that. Like I said, gives very much kind of that House of Spirit sort of feel. House of Spirit was where you would, if you controlled the value going into a free, you would basically craft a fake block to get not an arbitrary address. You would need to have something already there, but to get an address that is at least somewhat attacker controlled already into the free list so that can be reallocated. Same sort of primitive going on here, just less effort because these sort of allocators that get implemented tended not to have the same level of mitigation in place. Like with this case, they're basically just able to give it any pointer because there's no sanity checks going on.
This is a really nice example, a really nice simple example of corruption chaining or primitive chaining, because they're able to take that initial null-byte out of bounds right. It's a very like low capability type primitive. Like you said, often it's not even really exploitable. But in this case, they were able to take that to then basically corrupt a pointer to then get a more useful pointer takeover of being able to control the full 4 bytes of the first block for the free pointer. So yeah, it's pretty cool how this was exploited. It's not too often you see this type of issue so easily exploitable, though in embedded it kind of makes sense, especially because you're in more of like the 32-bit world. And like you said, it's a fairly common issue to see, especially when it comes to like doing things like null termination. It's a pretty big concern whenever you're dealing with C strings that, what if someone passes something that's not null terminated and then you use some API function on it like strlen that will keep going until it hits a null terminator. So you're like, okay, I'm just going to null terminate it just to make sure. But you often want to do that at the end of the buffer, and that's where those off by one issues tend to happen. So
yeah, it's
yeah,
a really easy mistake to make. Just thinking like I allocate this many bytes, and then later, okay, I can access it via that number, and you have to kind of really be thinking about it. And of course, C and like the standard library is a little bit inconsistent on whether or not you're getting a null terminator at the end of certain strings. Like just like on some of the functions that will take a bounce check, you'll get a null terminator as long as it didn't write all the way to the end.
It's pretty ambiguous which functions will do that and which ones won't. Yeah.
Yeah, like, well, both in that sense and just the fact that even a function that does normally, if it reaches a limit, it won't. Whereas I think it probably would have been better where if it reached a limit, it should have just saved the space for the null terminator. But that's a whole different discussion. The whole fact that there are these ambiguities and these things that are unclear just leads to these sort of patterns that then need to keep everything else in mind, and you see these bugs. And yeah, they did get kind of lucky in terms of what that null byte actually landed on and provided them. Because if that null byte did land in just the padding of an allocation, like if they did have an allocation that say they did like a 60 byte allocation, it just got rounded out to 64 bytes, as some heap allocators will do, you'd just be writing into nothing. Like it wouldn't have any impact. So they did kind of get lucky on that. And I mean, with a bug like this, you do have to get a little bit lucky in terms of either what you can where you can get it to write or where you can coerce it to write into. And that's true with like, poison, null-byte, and all of those attacks too.
Yeah, but in the embedded space, especially, the odds are more in your favor than they would be in many other modern targets.
Perhaps, but on the embedded space, you're also more likely to be running into devices that are big endian, and in which case this sort of override would have resulted in overwriting the most significant bits instead of the least significant bits. So again, would have turned into more of a challenge. So I'd say it's largely just luck rather than even more likely on embedded versus not. Although embedded is often lacking a lot of the mitigation, so there is that.
And that's the other thing. Yeah, if the allocator was hardened here, that could have prevented this, but it wasn't. So, and on the case of the big endian versus little endian, I think in big endian you could probably still exploit this. Maybe not as reliably, but I think you could still do it.
There's the potential for it, again, if you're lucky, but on big endian, like this sort of thing, if you're going to overwrite the most significant bits, what are the odds that that's going to be readable? Whereas it's almost always when you're just rounding out those last 8, last 8 bits, like that feels a lot more likely to still be within kind of user writable pages, just because of how things tend to get aligned. Whereas having something starting with a null-byte feels less common to me, at least, but I don't have the stats on, so maybe not.
Yeah, I mean, to be clear, like being able to go after the least significant bits is better. Like objectively, that's the more useful path. But I think it could still work the other way, but that's beside the point. So yeah, I guess we can start our train of Windows bugs. So up first for that, we have a Project Zero report on an integer overflow in the VrpBuildKeyPath function for containerized registries, which is used for siloed processes, for siloed applications or server silos. This is one of the more simpler Windows kernel reports we've seen in how the bug works from Project Zero, as the issue ultimately is just a dumb integer overflow when setting the destination buffer's max length. So, looking at the code here, it has this destination buffer, which is a Unicode string type, and it'll take the key name length, add it to the base path max length, and then add the size of or the length of a wide character, which is 16 bits. But of course, there's no checks to ensure that calculation doesn't overflow, and it's pretty easy to overflow as that maximum length field is only a 16 bit short. So by passing a large name, they can cause that calculation to overflow and wrap around the max length, which is used for allocating the backing buffer. Now, interestingly, despite what it might seem at first, this doesn't lead to memory corruption exactly, because that max length is also what's used for copying in data. So, it's one of those cases where even if you get the buffer to be allocated only at like 4 bytes or something, that's the max you'll be able to copy in anyway. But it can induce some interesting logic bugs where the string is terminated early. One of the possibilities that they mention is that it might be possible to break out of the containerized view of the registry via tampering with the path for the key, which is used for getting the namespace of that containerized registry. But if you can cause that to be empty by, making it so the backing buffer is like 0 bytes or whatever, that can prevent the translation of the real path into the containerized path, which it seems like might just silently fail and just use the real path instead of the container one. So, yeah, it's sort of the type of issue that you typically see in memory corruption, but it's leading to a logic issue. So that's pretty cool. When it gets to exploitation, it is mainly like talk about the possibilities. There was also a bit of discussion on whether or not this is considered a security boundary. I believe ultimately they'd said, yeah, after much back and forth with various people in MSRC, a decision was made. If a container escape works from a non-administrator user, then it would be considered privilege escalation and therefore serviceable. So, there was a bit of back and forth on that, but I like this report just because it's not too often you see integer overflows leading to logic issues like this. And like I said before, when it comes to these types of logic issues, they're ultimately nicer as an attacker because you don't have the reliability drawbacks that often come with memory corruption. So, from an attacker perspective, this kind of route is a lot nicer than going for memory corruption, even if you are, if you find memory corruption more fun. So.
Yeah, and that's sort of like, so we've seen a number of Project Zero posts kind of looking at the registry, and a lot of them have resulted in just this sort of registry or containerized registry escape and just other kind of registry shenanigans. Um, it's kind of left a lot of these bugs in that realm, and I do like it because, like I said, it is. I feel like in the future we are going to start seeing more exploits taking this sort of route rather than going for just complete ownage and like code execution and everything else. Doing a lot more of these subtle bugs, just as exploitation gets harder. This is, I think, where things are going to go, and it is more of a data-oriented, I guess, approach to it.
Yeah, you're not running into a lot of the mitigations that have been getting all the work put into them for the last little while. These types of logic issues are a lot harder to mitigate, and because of that, they're a lot more reliable too.
Yeah, and in fairness, like the trade-off there is it's also a lot harder to do things with. Like the power of this is not clear exactly. You get this one you don't often have, like I haven't run into like registry containerization that much in the first place. So it kind of limits the use case there, but I don't know. I feel like it is an underexplored area also, and therefore you might have a lot more primitives to work from. And like it is registry stuff, there's a ton that you can do inside of the registry. So like there would probably be a way if you were in some containerized registry to escape that and to get something more out of it. Although that is not an area I'm familiar enough with to actually like speculate on what that would look like. Nonetheless, I think it's a pretty fun bug, and I've enjoyed seeing these bugs out of the Project Zero team over the last, I don't know, feels like we've been covering them for about a year now or so.
I'd say that's accurate. And this one's pretty nice too, because some of the other ones we've covered were a little bit difficult to understand. They require understanding the nuances of the Windows registry. Whereas this one, it's pretty straightforward, even if you don't fully understand all the implications. The root cause is fairly obvious, so yeah. It's a pretty accessible issue. So, continuing with our chain of Windows bugs, we have a post from the Edge Vulnerability Research Lab, and I'll let Z get into this one.
And also kind of continuing with the accessible issues. So this post goes into a good bit of background, and at least to understand the issue, I don't think a lot of it is necessary, but I will step through some of it. Um, and the post is escaping the sandbox critically because this is a sandbox escape for impacting Windows on so they mentioned like every Chromium build, and that kind of has to do with how Chromium architects itself and how things work. They have kind of the image here of the browser sandboxing and the interprocess kind of set up here, where you have your main thread, the main browser, and then every like website you visit or whatever is going to have its rendering, and all like the untrusted JavaScript will, and whatever else untrusted coming from just the random website, is going to be processed in this separate process. In that process, they're just using the rendering process as an example, but they do gonna have other processes that might be started too. That's going to handle and parse all the untrusted data, and it has no access to the network, no access to the file system, no access to really anything you don't want a random person having access to. And instead, the only way they can get access to that is through their IPC calls back out into the main thread over these channels, and they can request access to certain things. One of the things that JavaScript running in the sandbox here can make a request for is through this web speech API. That's the JavaScript defined standard, allowing developers to either do like speech recognition work or speech synthesis work. So just text to speech work, and I'm sure you can imagine where a web speech API would go. And the way that gets implemented is the rendering process in JavaScript being interpreted. That's going to have just this IPC call to do it, and then that will go into like platform specific things over on the actual like main thread that's handling the IPC call. So the rest of it's kind of platform agnostic. And so ultimately on Windows, that's going to call into this ISP voice comm interface, create the speech synthesizer, and calls it with this speak method to actually do like a text to speech thing. And what's interesting there is, in order to create an utterance or like just have speech synthesized, it actually takes XML, which kind of surprised me, in part because I tend to use Firefox a lot, and Firefox does not support this, as it actually strips all of the XML tags out. But on Chromium, it allows all of these XML tags through, and that's just, it basically has this whole, they've got the speech synthesis markup language, which is used for text-to-speech engines, or Windows actually has their own, which is also supported in here. Does both, and they'll parse through for both. But the vulnerability is when it falls through. So if it doesn't find any of the speech synthesis, or finds some unknown tags from the SSML, that's speech synthesis markup language, if it doesn't find, or sorry, if it finds any tags it doesn't recognize, it's just going to fall back to their SAPI XML grammar, which is the Microsoft kind of special one there. But the idea of this is just, instead of only providing text that you want said, you can include information like the volume that should be set at, or the speaking rate for it. And I'm sure other things that are documented if you actually were to dive into it, but has this extra kind of functionality of XML that can exist inside of this input. And that input, this string, is being passed, this like volume string, or at least this example in here, that from JavaScript is being passed all the way into that native library that is running in the highly privileged, or at least more privileged, browser like main thread, or I guess it's the IO thread here, but it's running with all the privileges. It's escaped the sandbox, and it's passing this XML to be parsed. This untrusted data is being passed into the native code to now be parsed and do everything, with potentially having all the privileges. So a bug there would also be a direct sandbox escape. And given the fact that this is a post about browser vulnerability research, they did in fact find a bug there, and a pretty simple bug at that. What they've got is that's their parsing. It said this happens when if it doesn't detect any of the SSML tags or detects any that don't fit inside of SSML, falls back to SAPI, which is then where this bug is, and that's just doing like the generic XML parsing in the SAPI DLL library, and that has the struct XML tag runs through that and has XML attrib and sets the adders or attributes to, or creates an array, sorry, in this struct of just max adders. And that max adders is 10. The maximum number of attributes that allocates here is 10. And as you might be able to guess already, it doesn't do any bounce checking on the number of attributes. So if you have an XML tag with more than 10 attributes, when it's parsing that, it's just parsing until it doesn't find anymore. So it's going to grab more than 10 and it's just going to keep indexing into this array at 10, 11, 12, 13, just keep going because it just increments the num attributes value and indexes by that in the loop. So the bug itself is very straightforward. Send it too many attributes and it'll overflow. One of the fun things that they noticed with this is in their proof of concept, they immediately got a RIP corruption. So they were able to corrupt the saved return address, likely, because they wouldn't have direct access to the actual register. So they're able to corrupt that, but they didn't trigger any stack canary check. And they're digging in, like, why can't we, if we're corrupting this on the stack, which is what it seems to be a linear-ish overflow on the stack. They checked it, like this library's built with the stack canaries on. They even opened this up in IDA and saw the stack canary check. And of course, the issue turns out to be just, if you take a look at this XML tag structure again, they're inside of this attributes array. It's iterating through there, and it's iterating using the very next value in there. So as soon as they overflow attributes, they're going to overflow into num attributes, which then means the next loop, when it indexes into num attributes, it's potentially not going to be a linear overflow anymore, and they basically just by lock happen to skip over the stack canary and then overwrite the return pointer after it instead. So it does depend on actually being, I think it's a 24 byte aligned, as each of these XML attributes are 24 bytes, so you're kind of having impact in there, but core bug, provide too many attributes. They don't get into full exploitation. They just show, obviously, they could take over or hijack RIP, so very useful control flow hijacking primitive, but they don't take this to full exploitation. This was a bug they found through fuzzing, and they do talk a bit about their fuzzing and their fuzzing campaign, some things about that, because this was found both with actually, this bug kind of prevented getting deep coverage on their fuzzing, because they would basically just hit this bug, and then any of the mutations, anything else going on, just hit the same bug and didn't get any new coverage from it. But they talk a little bit about the fuzzing, but ultimately, that's where kind of the vulnerability and exploitation ends. They theorize about a couple options for how they could go forward on exploiting this, overwriting a pointer with the full keyword, somewhere else on the stack, because they do control that num attributes and they control where it's going to write on the stack. They could point this into another stack frame because it doesn't have to be a linear overwrite anymore. Could target something else, although they do call out that can be hard when we're talking about a 64-bit system. There's usually null bytes in pointers, and the strings that they're needing to use for the XML are wide characters, so they can't use any double null pointer, or that's just going to terminate the wide character array. So that does create some challenge, and they do talk about overwriting a stack value that's maybe aligned with the controlled length value. Toss out some options, but ultimately they don't take it forward, and they do see issues with kind of the routes that they've speculated about. Nonetheless, I think it's an interesting bug. It's also kind of crazy it's kind of an interesting study at just how something's deep functionalities can surprise you a little bit. Like, I wouldn't have known that or intuitively guessed even that there was some XML parser deep inside of the web speech API, or that was being handled by like the native library rather than being handled inside of the actual JavaScript or the renderer process that's sandboxed. And I would guess that a lot of people just, I don't know how old the web speech API is, but I would make a
It's
guess
very
that,
old because they
yeah,
said that this bug was in there for 20 years. So.
right. I forgot about that. Yeah, so fairly old thing. And yeah, I was thinking that the speech API was quite old, at least for doing speech synthesis. I'm not sure about actually like what all that library does with recognizing text. That might be newer, but I do remember it going quite far back. So the fact that it is quite old there, I could easily see it being one of those features that just kind of kept slipping through and nobody really thought about. And until you dig into it, you don't really realize that it's getting that deep and escaping the sandbox with this untrusted data. Because having, so I guess if you were to naturally write this, you might and go that route, but one of the rules for Chromium has been specifically avoiding like passing untrusted code outside of the sandbox or untrusted content outside of the sandbox. So the fact that parsing is happening, like it is just a little bit surprising and interesting to see something slip through for so long. But my feeling is that it's just one of those things that survived because of it being ancient. No one really thought about or realized it was there for a while.
Well, not only that, but I think part of it too is just because it's such a complicated thing that even if you did try moving this inside of the sandbox, you would be introducing a lot of attack surface as well. Whenever you get to these types of accessibility features, it seems to be the Achilles heel of a lot of sandboxing and security models in general, because it's not something that everybody uses, so stuff doesn't get caught as early. It's also not necessarily code that everyone wants to look at or deal with, so it's just kind of this big elephant in the room, so to speak, when it comes to security.
Well, I guess the
So
question
it's not too surprising on that side.
is this XML even documented though as part of like the JavaScript API? Because
Well,
like I
I don't
mentioned,
think it could be because you said Firefox doesn't do it, so it can't be a
exactly.
standard. Yeah.
That's why I feel like it's something that just kind of slipped through unrecognized as even being there.
Yeah, that's true.
Rather than some that like if somebody were porting it over, they may not even think they needed to do all of this other stuff because it's not necessarily recognized. I just pulled up the MDN here, but looks like I'd probably have to spend a little bit more time digging into it. I'm just looking
It's
at,
always fun trying to read these browser compatibility charts in the JavaScript documentation. It's just a real
yeah,
fun
like
task every time.
the example they have here. I don't see any mention of. I guess they do go through the utterance here, so maybe something gets documented there. But it looks like they're expecting it. You don't just pass in text, and what you once said is being passed in as a new utterance.
Which is the intuitive route. Like
Yeah,
that makes most sense.
like the
Um,
support for XML doesn't seem to really be there. So yeah, it seems like something that will have just slipped through, and it's a really simple bug, kind of indicative almost of the time in which this was probably written.
and on the note of the challenges with hitting the instruction pointer, that is like those are fair arguments. Like that's always trouble you run into when you're trying to overwrite pointers with strings. But where you kind of have that non-linear overflow where you can write into anything, like I'm sure there's other things on the stack that would give you good enough primitive to chain off of. So, but as you say, they don't really go into that here. But I did want to mention that.
Yeah,
Uh,
and this is like Microsoft browser vulnerability research team. They're not necessarily doing all the exploitation on it. Because one of the other things they talk about that I don't think most of us would be able to do is they were able to go recompile the SAPI DLL with address sanitizer. Most of us don't have the source to that as far as I'm aware. So they are doing some things, and like they talk about their fuzzing campaign, using like libfuzzer, or well, specifically libprotobuf mutator, but that's on top of libfuzzer. Uh, they're doing some things that maybe the average person isn't going to have access to. Still an interesting read though, but yeah.
yeah, like of course Microsoft is going to have the leg up on buzzing and targeting Microsoft
Yeah,
applications where
of
they have that
course.
internal tooling and stuff. Um,
It's actually
but
kind of
yeah,
interesting to see them talk about this, though. I was a little bit surprised to see the mention of like ASAN and stuff, just because we don't normally get that insight to what Microsoft is actually doing.
yeah, and that's one thing I've really appreciated about this blog over time. Like we've covered some other similar topics off this blog that give some nice insights into Microsoft's internal processes and stuff. Um, Yeah, I mean, I find it interesting though that this bug did survive for over 20 years because even if this is kind of in a obscure component that maybe its reachability isn't from the browser at least isn't very obvious, any like basic fuzzing would catch this pretty quickly as they proved. Um, like just having like more attributes than 12 or whatever, like that's a pretty easy test case to reach. So it's
Yeah,
kind of funny that it existed for so long, but I guess it's just like you said, it's just
you
it
have to
wasn't really
know.
thought about or targeted.
Yeah, it's one of those things that, like, when you know it's there, yeah, it's really easy to fuzz when you know that
The
functionality is
hindsight
there to be
2020.
fuzzed. Yeah,
Yeah.
exactly. It's just a case like it is kind of deep in there and hard to necessarily realize that, hey, we could or should be fuzzing this area. And there very well may be some other things like that lurking inside of JavaScript. Although now that this was found, I feel like a next step would be what other really old code are we calling into or can be reached like this, and doing some maybe some better taint tracking to see what libraries get hit or something.
Yeah, because there's almost certainly more than just the web speech. With accessibility, you have multiple different things. So
Although
yeah,
some
that would
accessibility is newer than others, so
yeah, but still, it's definitely a step that makes sense to take.
yeah.
Final thing I'll say, it's not really related to the blog post, but I do really appreciate the title, "A Bug That Speaks for Itself." Doing the punnery, I do appreciate that.
I'll be honest, that went right over my head.
I didn't really think about it until like you were talking and I was reading the title while you were talking about it. I was like, oh yeah, that's cool. So, all right. So with that out of the way, we'll get into our last topic, which is our final Windows bug out of Theory, being a wild copy in the ancillary function driver for WinSock, specifically its support for FastIO, which allows for communication with devices without using IO request packets or IRPs. That's not super relevant, but that's just the functionality that it's in. The bug is in the AFD send message ioctl, which copies a control message from user space into kernel. Something that's kind of interesting about this message, though, is how it's structured. So, sorry, I'm just trying to find it on the page here. So the way the message is copied in is it's basically a contiguous array of chunks. So each chunk will have a chunk size that's like the header of it, and then the data that follows. And those chunks have to be aligned, and it's being copied from a 32-bit process into 64-bit kernel. So it'll basically take the chunk size and then align it to an 8-byte boundary inside of the copy function. The problem is, as you might expect, since you have to add 7 in the process of aligning to 8, if the chunk size is set to a large value, like FFFB or -5, when the 7 is added, that'll wrap around and it'll get aligned to 0, which in the context of this code, ends up bypassing this check that bails out early if the remaining size is less than the align size, and 0 ends up, the large size ends up getting subtracted from the remaining size. The exploitation of this bug gets a bit interesting because there's 2 challenges they have to overcome. The first of which is that because of how the pool allocator works, similarly sized objects are going to be grouped together, and so the target object size has to be something that can be hit with the overflowed chunk, which is kind of a problem when what you're trying to get calculated is very large. And then also the overflow size needs to be manageable because you don't just want to trample over the whole heap. The first challenge at first looked kind of difficult because the size of the chunk that you overflow is ultimately derived from that int overflow size. What's funny though is because this is Windows and the way the API is designed is very conducive to double fetches, the user buffer is double fetched here. So it's read the first time to calculate the size and allocate the kernel buffer, and then it's read again for the actual copy. So they can abuse a talk to type scenario, time of check, time of use, to flip that chunk size between the allocation and the copy. And the second challenge is, with the copy being large, they would need to terminate that early so that they didn't trample over the heap. And the way they do that is pretty simple. Where this is copying from user memory, they can just set the buffer to point near the end of a page and then have the next page be unmapped memory, and that'll cause a fault before the overflow gets too far. From there, the exploitation gets a little bit Windows specific, so I'm not going to go too far into it. Sorry, you were going to say something there, Z?
I was just going to say, I really love kind of their use of the double fetch here, because usually we see double fetch as the core and key vulnerability in the attack, where it's like, you have a double fetch, so it allocates too small and then copies or something. Whereas in this case, they're using double fetch, like, it is a vulnerability in a sense, but they're using it as part of like their exploit strategy in order to uh, get one value or get one allocation there to work or whatever. It's just kind of a fun approach on it. And XCD80 mentions, I watched talk at HexCon, didn't know there was paper. Yeah, they do have the Hexacon talk also. I believe they go into a few more details here. I think they mention dive. It's right here at the top here. Take a quick look at the vulnerability they covered in the talk, and then they go deeper into the exploitation. And for what it's worth, like, it is Windows specific exploitation, but I don't remember it as being terribly crazy. They basically had this IO completion context that they could spray and also provided. So they did. Actually, one thing that I did want to call is they were looking specifically for an arbitrary decrement primitive, which I thought was an interesting choice. Often when we're talking about kernel exploitation, it's about getting that read right. So they had their route here with just the primitive by targeting. It was one of the thread objects that they were able to get. That basically
Yeah,
they had
it
the
was the kernel
decrement.
thread. The
Yeah,
kernel thread object. It had a field being the previous mode, which I don't know all
right.
the context of that, but if you set the previous mode to 0, it basically allows you to privilege escalate that thread, as I understand it.
Yeah, so I thought the approach was a little interesting. Sounds like that's a common thing. It's just less in my mind because I don't do the Windows exploitation, but I just thought it was a little bit interesting that they were going for that arbitrary decrement primitive instead of like the read write. But fair enough, still works, still a route to go.
Yeah, and they link off to a synactive post for that strategy, I believe. The IO completion context, I think, was them. And basically how they used that was the port field in that object. That pointer would be used to. It would basically decrement at that pointer when it was released in the context. So if you could overwrite that pointer, you could get the arbitrary decrement and use that to hit the kernel thread mode. What you mentioned with the talk to or the double fetch, yeah, it's a fair point. Usually, it is like the main bug of focus. Not only is it kind of cool that it's not here and it's playing into their strategy, but it's also a case where this bug probably would have been unexploitable, or at least a lot harder to exploit without that issue. So you kind of have two issues that are playing into making this a problem. So, and in Windows land, that's a bit more common, just because in Windows there's been a longer history of just directly using data from user space, whereas Linux and FreeBSD and like a lot of the Unix-based systems have been treating user as untrusted for longer, and they've kind of had that model down of copying the data into a kernel buffer and then validating and working off of that, and not going back for the data from the user again.
Yeah,
It does happen sometimes, but it's a lot more common in Windows.
yeah, it's well on Linux and on the Unix systems, like they have a lot more centralized control over all the drivers because they're in tree.
That's a good point
So
too. Yeah.
when they decide to do that, like say introduce like the user annotation or whatever, so they know to like turn off SMAP for those accesses. Um, in doing that, they're able to just go and like do that across all the drivers and implement. I don't know if it was done in one shot or if they did it over time or whatever, but on Windows, it's like they have this backwards compatibility where it's like all these drivers exist that just do that access, and they can't really just fix it everywhere all at once. I mean,
It's a
technically
lot
on
harder to enforce
Linux.
change across the whole ecosystem on Windows.
Yeah, and I think that's why like SMAP is still kind of an issue. I think they've had a bit more success with some core like SMAP access and not executing from userland, but yeah, SMAP just on Windows with so many different parties involved feels like it's going to be a while before that totally dies.
To be clear here, like SMAP isn't really the factor because they are copying into a kernel buffer and everything. It's just that they do it twice. That's what leads to the double fetch issue. It's not your classic double fetch where it's like they're directly dereferencing from user space on
Yeah.
every access, but it's sort of similar in how it's taken advantage of. So yeah, obviously we've had a fair amount of Windows bugs in the episode, so that's why we titled it "Bundle Windows Bugs." That is all the topics we have for today, though. So unless you have any last minute thoughts, C, I think we'll wrap it up.
Yeah, no shout outs, though. Again, make kind of the usual requests for feedback, especially from those of you who are on here live. Regarding if we do move to kind of a record only and drop the stream, in favor of being able to record and spend a little bit more time polishing up these episodes. We've talked about that on the past streams, but again, we'd appreciate any feedback. You can drop that on Discord, emails on our website, or whatever. Any way you could get hold of us.
Yeah, pretty much any channel we're on. Yeah, feel free to leave it there. We don't have like a dedicated section for that. You can just leave it wherever. So yeah, with that said, thanks goes out to all of you for listening. If you want to go back and check out past episodes, they are on YouTube, Spotify, Apple Podcasts, and more on Anchor. Feel free to join Discord and follow us on Twitter. Links for those are down below or in the chat. And with that said, we'll see you next week.